Assalamu alaikum, guys. Welcome to the new lecture. This is our lecture 5, probably. In our previous lecture, we have dealt with, or we derived the signal power, right? Now, in this lecture, we will derive the noise power. We'll derive the noise power. So, if we remember what was our previous lecture? In our previous lecture, we have seen complete signal, which contains the signal power and the noise power. So this is our lecture 5. Okay. So in lecture 4, this is the one we have seen, right? The signal power. This one here. This was our signal power. This one. This is our noise power, right? So signal power, we already simplified our signal power. Signal from the signal component, we derive the signal power from the signal component, and from the noise component, today we'll derive the noise power. So what is the noise component? Minus infinity to plus infinity, nt minus tau, h tau, d tau. Okay. So we'll go back to our today's. Go back to our today's lecture, where we will derive the noise power. Let me draw the schematic diagram that we have already drawn. That we have a signal x t, right? The signal was, noise was added in t, passed through a channel h t. After passing through the channel, we do the sampling. The received signal is RT, right? And here we do the sampling. That is the schematic diagram we had before, right? So we have seen our received signal RT have two components. One is the signal component and another one is the noise component. From the signal component itself, we draw the signal power. Now we will deal with this noise component. Okay. Now here, this is our signal NT. So the signal component after the NT here, here we have to make it as n of something, n, for example, n tilde, just to make it different notation. So this one, the signal component denoted by n tilde, which is here, this one. We have seen our total component. One is the signal component, one is the noise component. So noise component is minus infinity to plus infinity n t minus n t minus tau h tau d tau, right? Now we see here is a n t component. Capital T means actually this is after sampling. So this is after sampling. This one is actually after sampling, not here. Not here. This one is here. This n tilde is actually here after sampling at t. That's why we have this modification of t. Before it was small t, right? Small t. At here, small t. But here it becomes n tilde capital T. That's why. Okay, at this point after sampling, that's what we are actually trying to say. Okay, now some assumption. We assume that this noise component n has a specific characteristics, right? What kind of characteristic this is? Additive, wide, Gaussian noise. That's actually we assume before that the noise is adding in our signal, that is a additive noise because it's simply added. It's a white noise is a Gaussian. Its distribution is a Gaussian. So this is a additive white Gaussian noise process. So it's a Gaussian noise process. Now, because this Gaussian noise process is passing through a LTI system, LTI, linear time invariant system, which is actually our filter. So the output here will also be Gaussian. Means if a Gaussian process is a Gaussian, if a Gaussian process pass through a linear system, the output is also a Gaussian. And Gaussian random process, Gaussian random process. Process means it's actually series of something. It's a combination of lots of small variable. Now this random process is sampled here at t. Because it's a sample, so at the sample output of the sample, this will also be a Gaussian random variable. So this n tilde, this one is also a Gaussian random variable because it was sampled. Okay, we have seen from the definition of Gaussian random process that Gaussian, we can say some process is a Gaussian random process if all its event or samples are also Gaussian. Say previously we say a Gaussian random process NT is Gaussian if its all samples or events are also, for example, NT1 plus NT2 blah, 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 plus NTK. All the if this NT is a Gaussian random process, if its joint distribution means its small event or samples are, they itself are Gaussian random process, and these events are called the random variable, such as this. Okay, because it's a Gaussian random variable, we will have its two values. So it will have a mean value. It has a mean value, mean of n t. The mean value of this noise is 0, and its autocorrelation will give us autocorrelation. So autocorrelation, because this is a white stationary, we discuss all these properties in our noise additive white Gaussian noise section lecture probably 3. So this autocorrelation in t plus tau, which is actually is a autocorrelation r in tau, is, we have seen the autocorrelation of Gaussian random process is in eta 0 by 2 del tau, because that's why we came to the decision this is a white noise, because we have seen that this is a its distribution is in eta 0 by 2, so its distribution is as a constant value having a sigma tau here. This one, the distribution, the probability density function PDF of this autocorrelation is looks like this, means it has a fixed value, it has a constant value. That's why it's a white noise. That's we actually discussed before. This part we already discussed as a noise properties. So we can say this is a zero mean. This is a zero mean. Now this is a Gaussian distribution. So for Gaussian distribution, what a Gaussian distribution look like? Let us see the properties of a Gaussian distribution. These things actually is supposed to know in a in your previous RSP course. Alright, so let's recall. Probably you already know it. So the Gaussian distribution looks like this, which has a mean value mu. So if it's a function x, so the function x has two value. It is expressed by its mean value. It is expressed by its variance, sigma square. So this is the mean. This is its variance. Variance is nothing but the power. Okay, so we can express this signal, this function, this function x, if it's a Gaussian distributed, so it's 2 pi sigma square e to the power minus x minus mu square by twice sigma square. This is the Gaussian distributed function. Any function Gaussian have, this is the function. Okay, we don't need actually this one, just to know how the distribution looks like. Okay, now we are saying the here. Now we can express its mean and we can express its variable. Now we find the mean value, right? The mean of this Gaussian. We find that the mean value is 0. The from the autocorrelation we can find its probability density function, which is actually the PDF, probability density function, which has a fixed value. That's why you call it a wide distribution, right? Okay. Now, because this is a Gaussian, we have seen its Gaussian distribution is expressed by its mean, and its variance or the power. We find that its mean value is 0, right? It's have a 0 mean. We can actually check it. What is the how to find a mean value of this Gaussian, right? So this value, this one, this. What is the mean value? We know theoretically its mean should be 0. Let's see. So the mean of in tilde, which is actually after the sampling, right? After the sampling. So how to write it? Mean value will be minus infinity to plus infinity. So we should have mean of the whole signal, mean value of our signal. Our signal minus infinity to infinity n t minus tau h tau data. This is our mean value. So mean is a linear expression. This mean is a linear expression. So what we can do, we can write, we can take it inside mean of n t minus tau. Also, mean will be applied to this h tau. Now, h tau itself is a deterministic value. Means what is that h tau? H tau is a characteristics of the filter. Filter is a physical phenomena. Filter is a physical stuff, right? So this h tau is a physical value. Means it has a constant value. It has a fixed value. So its mean will be the value itself. So we are not changing it. Now this uh, this expression expected value, we know the expected value of n, we know the expected value of n is 0, means this will also be 0, means the whole the expected value of the noise which will be after the filter is a 0. So it's a 0 mean. 0 mean here at this point, at this point, at this point. At this point, the signal will be 0 mean. Now we already done the 0. What should be the variance? So the variance is nothing but n tilde square. That's the variance. Okay, we actually can write that this absolute value, but we know this is, we assuming this is a real quantity, so it could be directly square of it. So we can write it, we can rewrite it by the expected value of n tilde into n tilde, right? So we can write it expected value of minus infinity to plus infinity. We know n tilde is n t minus tau h tau d tau into itself again, n, okay, minus infinity to plus infinity. Here, instead of writing tau, we will write tau tilde, because tau is a variable. So just to distinguish from one to each other, we just writing it as a tau tilde. So because it's a variable, we can write it tau tilde d tau tilde, closing the bracket. So what we can do, we can take the integration outside, both of the integration outside. So minus infinity to plus infinity, again minus infinity to plus infinity, expected value of n t minus tau and n t minus tau tilde. Remember, we did the same thing, expected value for h and h tau and h tau tilde. They are deterministic, so expected value do not apply to them. So h tau tilde d tau tilde. Okay, we can see this expression. This expression is nothing but an autocorrelation. This expression is nothing but an autocorrelation. Remember, autocorrelation of E, for example, the simplest form. What was the simplest form of autocorrelation we have seen? N t plus tau, plus or minus tau, whatever. This was the autocorrelation formula, right? So what is the autocorrelation of this value? Autocorrelation is, this is n eta by 2 del t, right? We have seen it before from the previous this one, from this one, yeah. This expression means this guy, this is also an autocorrelation. If we rewrite this autocorrelation formula, what it will be look like? So it will look like E of n t minus tau and t minus tau tilde. What is the autocorrelation function? Is nothing but eta 0 by 2 del t minus tau. Sorry, del tau minus tau tilde. It's actually same thing if I write it other way. I2 del tau tilde minus tau. Same thing. This expression, this one. So rewriting the whole stuff, like rewriting the whole stuff, we can write it. Okay, we can write and eta by 2 so eta by 2 minus infinity to plus infinity minus. Okay, let us so rewriting here. So eta by 2 minus infinity to plus infinity minus infinity to plus infinity. So this amount we know, this is the amount. So h tau tilde del tau tilde minus tau d tau, right? D tau tilde d tau, or d tau tilde, whatever. Tau tilde. Here, assuming this is this one is the inner integral inner integral with respect to tau tilde, and this is inner outer integral with respect to tau. So what we can write? We can write this signal we can write it minus infinity to infinity. So h tau minus infinity to plus infinity. We are considering all the tau tilde together. So h tau tilde del tau tilde minus tau d tau tilde. Let's make it a together. So this is one equation into d tau. Now this is a formula. This one is a formula. What formula? We know from del equation, the shifting equation of direct delta function. We know from shifting property of delta function. What do we know? We know that minus infinity to plus infinity x t del t minus tau 0 dt is x t0. So we will compare it with this one. We can find what? we can find that this equation looks like minus infinity to plus infinity h. This will be looks like function of h t, which is actually h tau. X is the this one, this x function is this one, t0 function is the this one. So this t0 is from this 0, which is actually tau. So h tau d tau. That's actually our equation. Means what we can find. We find that the we find the we have missing one amount. I miss this amount everywhere. Yeah, this one. Okay. So it was here n0 by. So it was here. So we can write it eta 0 by 2. So we can write it here eta 0 by 2. So eta 0 by 2 minus infinity to plus infinity h tau square d tau. We can write it eta 0 by 2 e of n. Here this En is the energy of the filter. Okay, so we find the noise power. We find the noise power or the variance. We find the noise variance because it's a sigma square equal to eta 0 by 2 E n, the total noise power. Okay, so we have derived the signal power, we have derived the noise power. Now we can derive the signal to noise power ratio. We will derive it in the next class or next lecture. Assalamu alaikum.